It's a pleasure to be here. Okay, so yeah, once more, don't be shy, ask any type of question whenever you want. So I will give some lecture about flavor physics, and just before starting, let me just give you a sketch of what I plan to discuss. So my idea would be basically this course will be in 3 separate weeks. So we'll have a few lectures, one lecture today and tomorrow. Then we have other lectures on Thursday, Friday, the second week, and then the third week. So the first week we will do first an introduction to flavor physics in the standard model, where I will try to reduce the main aspects of flavor physics in the standard model, and I will focus especially tomorrow on aspects related to QCD effects, which you have something not really directly related to flavor physics, but is an important ingredient of flavor physics in the quark sector. Then I will also discuss quark flavor phenomenology. Okay. This is the first part. The second part, I will focus on the other hand on the flavor physics in the electron sector, and also on flavor models, which is already something beyond standard models which try to explain the flavor structure we observe in nature. And finally, in the last week, we will discuss flavor physics beyond the standard model. Then we will discuss various hypotheses of dynamical and flavor sensitivities of flavor for beyond standard model scenarios. Okay, so these are the 3 things which are somehow independent, so even if you get bored with QCD, and if you're more interested in the standard model, certainly the next week will be more important. Okay, so let me start with some probably really basic stuff. So, più grande? Okay, sorry. Okay, I'll try to try it. Let me start with some very basic things. Okay, so in the standard model, is it okay like this? So the Lagrangian standard model has basically 2 sectors, a gauge sector and a Higgs sector. Till few years ago, we would always say the symmetry Higgs sector, we don't know what it is. Okay, we know that it is a Higgs, and at least in the first approximation, certainly everything is described well by the Higgs mechanism. Now, in the Higgs sector, okay, if we look at the Lagrangian, we have the following term for the fermion. Okay. Where we sum over 5 different species of fermions: the extended quark doublet, urite, diorite, the lepton doublet, and the lepton singlet. And so we have a sum over the psi, but we also have a sum over 3 indices, which are the flavor indices, and this sum goes from 1 to 3. Okay? And then, of course, we have in the gauge sector we have the manifold for the gauge part. Okay, this is maybe I should sum it, put it as a sum over the 3 different gauge group. Okay. I think that like this in general terms. Okay, here I guess you know what I mean. What I'm concerned is about the second sector. So here this is a covariant derivative, and you see, as far as flavor physics is concerned, in the gauge sector there is a big flavor symmetry, because this index is just a dumb index in which we sum. Okay, this corresponds to a big symmetry. Okay, so if we ignore for a moment the Higgs sector, in the gauge sector, the sector of the standard model based on this symmetry, we have a big global flavor symmetry because we have these 5 different species. So the 5 species are differentiated according to the gauge quantum number. Okay, so these 5 fields have different gauge quantum number, but as far as the flavor index, they are completely identical. So we can, if I make this transformation psi going to I, where this is a unitary matrix, okay, this kinetic terms remain invariant. So I can do this for each of the 5 different things here. So we have a U3 to the 5 flavor symmetry. Okay. This is the flavor symmetry defined by the gauge sector listener model. Let's give a closer look. As you know, whenever we have a UN symmetry, UN means unitary matrix, we can always decompose, extract a global phase, a phase which is independent of the mixing, and then a special unity transformation. So I can always write a UN symmetry as a product of a U1 symmetry times an SU and symmetry. So if I apply this here, it means that we have 5 U1 symmetries times 5 SU3 to the 5 symmetry. Concerning the U1, so the U1 are really global transformation of the different species here. And so some of them are familiar, so let me put them here. So clearly, here, I mean, these are defined as global transformation independent for U, U, D, and so, but I can reorganize them in the following way. I can introduce baryon number, lepton number, either charge, which is the only one which is then gauged, and then other 2 U1s, which I will comment. So here for Q left, Q right, D right, here the following. So baryon number is of this one, no, lepton number is this one, either charge is this one, I hope so. 1, 6, okay. And then and this baryon number is not broken by the Yukawa interaction. So when we introduce the Yukawa interaction, we see that actually this symmetry is not broken. Also, this symmetry is not broken. This is also not broken by the Yukawa interaction, and it's actually is gauged, and thanks to the presence of the Higgs field. And finally, but is spontaneously broken by the Higgs field. Then we have other 2, which I can define this way. One is conventionally called the checking symmetry, and another one, I should just call it U1 prime. And I can define it so here, no charge, maybe charge plus 1 to the right, charge plus 1 to the right, and here no charge plus 1. And you can check as a very simple exercise that this set of assignment is equivalent, so it's just a reshuffling of the initial symmetry where I assign different charges, completely independent charges to the values field, okay? Okay, maybe this symmetry here, it's this symmetry and these are the 2 symmetries here are broken.
Sorry.
Yes.
The second U1s you've written, I cannot see.
Basically, no assignment for any field except E right.
The name, U.
U1 prime. I don't think nobody really proposed a good name for this one. And we don't know even if it plays any role, so this is why I don't have any special.
Is U1?
Prime.
No, then.
What? Sorry? This one?
Yes.
This is PQ, stands for Pechegrin.
Okay.
Because this actually has been used. And I will come back to this in a moment. So, now let's look at in the Higgs sector, we have the, as you know, here we have the pure Higgs self-interaction, the Higgs interaction with Higgs, but then we have the Yukawa interaction. the U-curve interaction. I write it this way. This is the interaction. That is the interaction that break the flavor symmetry in the standard model. Breaks this huge symmetry. So you see, this is a huge symmetry because there are each SU3 has a generator, and then you have 5 times SU3. So it's a huge symmetry, and it is broken explicitly in the standard model by these 3 interactions, the so-called U-curve interaction. I put here all the indices just to show that this is the interaction that really carries on flavor and not trivial flavor indices. And you see immediately one thing is related to this U1. You see that here I have only, this is the conjugate of the Higgs field. Okay. Here in the standard model we have only one Higgs field, and it's conjugate. And so basically we can compensate only for one non-trivial, so that clearly binary number and lepton number are automatically satisfied because of this assignment. On the other hand, considering the other 3 U1 symmetries, there is one that is the hypercharge, which actually is the same. If you look at these terms, this term and this term, violate, if I don't put the Higgs, violate, they have exactly the same hypercharge assignment compensated by the charge of the Higgs field. Okay, so I can deduce, if you want, the charge of the Higgs field and the hypercharge to get this term invariant. Okay. If, for instance, I consider a model with 3 different Higgs fields, I could compensate different U1 structure of the different pieces here. So, for instance, suppose that I have, okay, in a not too exotic model, 2 types of Higgs. Okay. One Higgs that cap only to the down, here, and another one that cap only to the up. And you see that if I give to the Higgs field the U1 charge that compensate the charge of the right and the right, which is exactly the 2 fields which are charged under this symmetry, I could maintain unbroken this U1 symmetry. Okay? And actually, if I have 3 different fields, so let's say H1, H2, H3, I could arrange their U1 charges not to break these 3 U1 symmetry. So this is why we will come back to this point in the last sector lecture. These U1 symmetries are related to are interesting in models with the multi-Higgs. Okay? Because they really could be not broken by the U-curve, but broken eventually spontaneously by the Higgs field. Am I saying something too complicated? Is it clear? Okay, so now let's remain within the standard model. Okay, so within the standard model we have this interaction that breaks the flavor symmetry. So, as I said, these U-curves are non-trivial metrics in this SU3 space, and of course they are not Hermitian matrices because they are associated to operators which are not Hermitian. So they are generic to diagonalize them, and as you know, to diagonalize them we need generically 2 independent matrices, so we can always decompose them in the following way. So we need 2 matrices to diagonalize, for instance, YZ. this is. Okay, and I can do the same for the up. And the same for the lectures, okay. What are these guys? Well, of course, as I'm sure you know, these are the eigenvalues of the Yukawa coupling, which are related to the masses of the fields in the model, and with my normalization, the Higgs value is b over square root of 2, where b is 146 dB, no? The standard notation. And so, with this normalization, these lambda I are the masses of fermion I divided by v square root of 2. And I mean, to determine this matrix, okay, guys, if you are not familiar with the simple linear algebra, to determine this matrix, what one has to do is to look at the Hermitian combination of Yukawa couplings. So, for instance, if I look at YD dagger, this is an Hermitian matrix, and this is indeed diagonal. Okay, and that's to be lambda d squared. And well, more precisely, this is modulus of lambda d squared, and these lambda d are not really well defined, okay? They are not defined up to phases that can always be reabsorbed to phases of these unitary matrix. This, on the other hand, by construction has to be a real eigenvalue, because this is the Hermitian matrix. So the only things which are really fixed are the modulus of the only things which are phase convention independent are the modulus of the eigenvalues of the Yukawa coupling, which are really the physical, related to the physical masses of the fermions. Okay, this is just a trivial notation. Now, given there is this SU3 symmetry, SU3, sorry, the thing you have to not forget is that we have this SU3 to the fifth Clever symmetry in the Gibbs sector. Okay. Given the rest of the model is invariant under this SU3 to the fifth symmetry, we can always redefine the field using these invariants, choosing a convenient basis, trying to diagonalize these invariants. So, what happens if I make transformation under this SU3? Well, for instance, my field Q left get transformed into some new Q left, okay? My U right get transformed into U, and so on. So, for instance, if I look at this term here, that term in there get transformed into left. Okay, and if I look at the other one, I get so, coming back to this decomposition, you see that if I choose, for instance, UD and UU to be exactly this matrix that diagonalize on the right YD and YU, I can always automatically choose a basis, okay, where YD is the diagonal on the right, and the only thing I cannot diagonalize simultaneously is on the left, yd and yu, because I can choose only one independent matrix, because I have one type of field. For this Q left, hope it was obvious. Q left is it's a doublet, okay? You think like this is the electron doublet, while you right and you right are singlet and S2. So I have the freedom to choose only one matrix on the left, so either I diagonalize yd or I diagonalize yu, okay? So for instance, we can always choose a basis, okay? We can always choose a basis, and of course in the case of the electron, my freedom in SO3 to the field in the electron sector allows me to always work in a basis where this is diagonal. So we can always go in a basis where, for instance, yd is diagonal, yu is not diagonal and is treated as a unitary matrix minus lambda u, and what is diagonal. So what is this B? Well, this B is the mismatch between these two diagonalization matrices of yd and yu on the left, okay? On the left, because, as I already said, in the case of gauge interaction allow me to make only a rotation of up and down, the doublet. So I should make the same rotation not to disturb gauge interaction. And so either I diagonalize this or I diagonalize that. In particular, with this choice, what this matrix is, B is defining the matrix in that way. I have diagonalized lambda t, so I have rotated my field by this matrix here. So this is nothing but u left b darker u left u. Okay. And this, as we actually this is conventionally called darker. Okay. Because V, okay, with this definition is the Kabib-Kobayashi Pascal. Okay. It's and one can prove very easily that this is we will now examine all the properties of this matrix. So this again you see it here very clearly is the mismatch between the left-handed one is the different orientation in the left-handed SU3 less space. So if I look at this group here, is SU3Q left prime SU3 right prime SU3 right, okay, times the electron sector. So what the CK matrix tell us is the different orientation in this group space of these two vectors, yd and y. Okay. Okay, so this is basically a matrix. Okay, probably you already seen it several times, but it is good to see it in this group type perspective. And so let's look at some properties. Let me see if I use the right convention. Yes. Okay. Let's look at some properties of this matrix. Now, before that, let me stress the one point, which is very easy but important. So, clearly you see that the CK matrix and the eigenvalues are tightly related. They have both properties of these coupling, yd and yu, which appear in the interaction. And so we'll now discuss all the properties of the matrix that control the mixing, but let's also give a look to the eigenvalues. So the eigenvalues, as I showed you before, are related to the masses of the quarks. So let me give you just some numbers, okay, which are the eigenvalue of lambda u, which is the one in the top sector, which is the one more hierarchical. So these a diagonal matrix, it's and so, as you know, the masses of the cores are random quantities, so let's evaluate them at the scale, at the realization scale of the order of the x expectation value, v. So, at that scale, the value we get are the following. 6, 10 to the minus 6. Is it too small? Okay. I tried, then I forget.
The memory is
6 to the minus 6, 3, and to the minus 3, and roughly 1. Okay. And this is interesting because you see, experimental, so these are just numbers experiments, and I mean, probably most of you know that, but maybe you have worked on some very formal topics in your, maybe you forgot about phenomenology, which is important. You see, that phenomenology tells us that you observe a tremendous hierarchy in the masses of the quark, especially in the masses of the A. The down and the left are slightly less hierarchical, but still, there is a hierarchy. There is a hierarchy basically of 5 orders of magnitude, even a bit more, which is tremendous. Okay? And maybe it's telling us something. And we will come back on that in the second lecture when discussing models. Okay, so this is just to keep this number in mind. Now let's look at the properties of the secant matrix. So, the matrix is obviously unitary because it's the product of two unitary matrices. I obtained it as a product of unitary matrix, so it's unitary. And yeah, okay, sorry. And before looking at the properties, let me also show you where these matrices usually appear. You find it in the textbook. But in the textbooks, often you find this matrix is the one that controls interaction of the quark to the lambda, okay, the famous charged current interaction. It is correct. Indeed, I show you that using the SU3 invariance, SU3 to the 5th invariance, I can choose a basis where under this diagonal, under U is the diagonal times B, and under this diagonal. So this is clearly not a basis where all quark, I mean all these interactions are diagonal, but this is not diagonal. Because this is not the mass eigenstate basis for all the quarks. Actually, it's the mass eigenstate basis for the dark quark, but not for the dark quark. So in this basis, okay, if I look at my charged current interaction from the gauge sector, this is given by well, before the interaction with the W is this one. Just okay. This is just the interaction part. And I want to write it this way to show that it's manifestly flavor invariant under that symmetry, or manifestly flavor blind. Then, if I look at the charged current interaction, I get so here this is at the sigma matrices. This is then let's see. Yes, still So, in the basis, where the matrix assumes this form, that is the interaction which is still the diagonal. Now, if I make an independent rotation, okay, now to diagonalize both down and upward, I need to rotate differently up and down in the same multiplet. So I cannot, the discussion cannot diagonalize up and down with a global rotation. So I will now rotate only U left, I, okay, to diagonalize here. So with that rotation, because I want to diagonalize the master of the integral interaction here, only the master, of course, I can diagonalize. And so we rotate the U left in form way, so U left in order to absorb completely of this matrix. Okay, so if I can make this transformation, the interaction with the Yukawa that was Daga. Okay. See, this is not the full Yukawa interaction, because this Yukawa interaction is also a charged current path, because the Higgs we want as the Boston-Boston component, which is charged. But I'm just interested in the neutral component, so it's in the here H. So this part becomes diagonal, or I feel better, I'm interested in the component that get the value, okay? So here, in this case, I get U right. Okay, so now I am the eigenstate basis of the upward, and what happens when I do this transformation, then here it reappears the second matrix. I know this, which is a trivial exercise, because I want to stress the following point. You see, the secant matrix has appeared here just because we wanted to diagonalize the Yukawa interaction. But the origin of the secant matrix actually is the secant matrix is one part, okay, related to the Yukawa interaction, is related to the misalignment of the Yukawa interaction in Plano space. Okay? And for our convenience, it's often convenient to put it here because we want to work in a basis where the morphine are the mass against basis. But the secant matrix is not a good with gauge interaction. Okay? The secant matrix is here because we prefer to use a certain basis for Yukawa interaction. But it originates from the Yukawa interaction. So if I set to 0 the Yukawa interaction, so in the limit where I set to 0 these y terms, okay, actually there is not any more preferred basis in the Yukawa sector, so this matrix is defined. Actually, it becomes dual identity because I do not have any preferred basis in the whole space. Okay, so I want to stress this point. The secant matrix really originates from the Yukawa sector. And it's intimately related also to the structure of the Yukawas, also to the eigenvalues. So I'm stressing this because when we will discuss hypothesis beyond the standard model, I mean, we should not only keep an eye on the secant matrix if we want to protect the secant matrix to receive large correction, given that this is well measured, but we also have to keep the two problems goes together, the problem of the matrix, the secant matrix, and the problem of the eigenvalues. Okay, so the matrix appears here if we want to work in the mass against basis. Okay, so now this is really when this U is related to the mass against state. And actually, here this type of interaction is the way we measure most of the elements of the mass. So let me take a few comments now on the size of these elements, of the experimental size of the elements and how we measure them. So the matrix is, okay, convention is written this way. Given it appears in this form, is usually written as BUD. BUS, BUD. Okay, just a notation. Now, experimentally, if we just measure, measure observable sensitive to this type of interactions, in particular the case of force and force where we have a charged kind of interaction, we can measure the strength of this interaction, which beside the gauge coupling is related to the size of these elements. So the size of V UD, we can measure very precisely from transition of the type U V. Actually, these are two very light forks. You can worry how we can extract precisely information about this type of transition, given that the forks are always bound inside the nuclei. But maybe we'll come back to that tomorrow. In certain nuclei, because of symmetry argument related to the character perturbation theory, to the fact that the fork masses are small, we can determine very precisely this type of transition in the so-called super allowed Fermi transition, which are nuclear decay, and from that we can measure the Cabibbo angle very precisely, this side very precisely. We can measure also the US rather precisely from S to D transition, which are actually measuring K decays, K to 5 electron decays. So these two together allow us to determine the Cabibbo angle. Sorry, I need to tell you what the Cabibbo angle is. Well, as you probably know, this matrix, okay, I forgot to say which are how many independent parameters we have in this matrix. So this is a unitary 3 by 3 matrix. Okay. So a unitary 3 by 3 matrix in general has unitary has n square independent parameters. This, I guess you know what, you don't know what, this is just 2n squared for a generic n by n complex matrix minus n squared related to the unit condition of unitarity, so this is just n squared. And this can be divided into n plus 1 cases, okay, and minus 1 rotational angles. This is called Euler angle, and in our case these are 3. And concerning the phases, we still have freedom in rotating the relative phases of the force, okay, because this is related again to the SU3 symmetry I told you before. So we have 5 independent relative phases among the fork, and so in the case n equals 3, this is just 1. So we have 3 real parameters and 1 phase. Okay, it's just a linear algebra that is worth to recheck it as an exercise. And so the Hessian matrix has 3 real plus 1 independent physical parameters, 3 real angles and 1 phase. And so we can always write in this form we want the rotation on the axis S12 times, usually conventionally it's depicted this way. Convention. So this is a rotation on the axis S13. With the phase delta. What I mean by this is just a rotational matrix of this type, S12. So this is just cosine sine, okay, in the 1, 2 sector, and similarly here in the 1, 3 sector and in the 2, 3 sector. You can see here that actually there were only two, the two generation model, there were no circulating phases, so we can only shift the circulating phases in the more suppressed transition, which turned out to be the one related to the 1-3 mix. So is that we put the phase delta here, and so the rotation in the 1-3 sector is, this is where we put the delta, okay. and sorry, and then this is now experimentally we find that this why this rotation is interesting because these elements S1, 2, so the rotation in the 1, 2 sector, the rotation in the 1, 3, and in 2, 3 sector are numerically quite small. Indeed, it's you probably have seen in the.
Sorry, one second. From your case, where you went,
Sorry?
and you went from the 9 parameters to only 4 parameters. And then it's squared to. You have n squared,
Yes.
which are like, and then you.
This is some of these tools should be n squared.
Yes, yes, but the argument of why you subtract -2 and -1. Okay.
Why subtract this one?
Yes.
Because so these are 6 phases, okay. I subtract 5 phases which are the relative, so you see this matrix is always of this type, okay? Mixing between one up-type port with one down-type port. Now, if I make a notation, okay, if I transform UR into just the port field UR in these phases, okay, this is something I can do without just redefining my field, and I can do it for all the 6 ports here. One is just a trivial shift that will not affect the matrix, but all the 5 relative shift basically can redefine the 6 phases here. Okay. Okay, and so this is why we get this structure. And so experimentally, it's convenient to expand this matrix, treating a small number, this S12, S13, and S23. So let me define S12, I define it as lambda, S23, I define it as A lambda squared, and S13 e to the I delta, I define it as A lambda 2 rho minus I eta. Okay, where A is a parameter of order 1, rho is also parameter of order 1, while lambda is a small parameter. It's turned out to be 0.24 and is related historically to the equalizer. So this matrix, if I do this expansion, becomes 1 minus lambda squared, lambda, A, lambda 2. Here I have minus lambda. Lambda squared. And 1. Okay. Plus, you see, I can always take this as a definition. I can always take this as a definition. If I take this as a definition, if I use what I just erased, this is perfect. Now I can then expand everything in power of lambda. Here I'm making an expansion, so I'm making an expansion up to lambda to the 4. Because lambda is the only really small parameter in this case. So, coming back to what I wanted to say here, so measuring precisely VUT and VUS from this type of transition, one can determine precisely the value of lambda, and it is known to very good accuracy at the level of Q per mil now. A is measured very precisely from VCD, which is measured from D to D, the case, and this for sure we'll discuss about the case tomorrow. So from this we determine precisely A. Now with a worse accuracy, Q at the level of 1%. And finally, VUD is determined again from VD gain by V2 too far, but here is a term which are much more uncertainty at the level of 10%. So I'm telling you this just to let you understand how well we know these terms, which are called the parameter that control flavor in the model. Note that, you see here, I tell you, we can measure extremely precisely these elements to the modulus of these elements from B and K, okay? And also told you that in a model independent way, we have only 4 independent parameters that parameterize this matrix. All the rest are just trivial bases that can be interpreted. So, question for you. I mean, if I measure, so if I have a matrix that depends on 4 independent parameters, if I measure 4 modulus very precisely, do I determine completely the matrix? See, it's simple. Incredibly. Sorry? The things generically is not the problem, because you see, it's, in general, with 4 moduli you can determine completely the matrix, because you see the phase appear here, it also control the model, okay, appear in the module here. However, these 4 which are selected here are not all independent, because they are VUD, which appear here, VUX, and VUB. Now, the unitarity condition, that is V dagger equal to the identity, implies, if you apply that VUD squared plus VUS squared plus VUB is exactly equal to 1. So the sum of all the elements along the row or along column, the modulus, the sum of the modulus squared is 1. Okay. So here, of these 4, 3 are related by 1 unitary relation. This is why I told you these 2 together I use them to determine lambda. However, if I could measure very precisely the modulus of this, and that, okay, this subset here, okay, very precisely, infinitely precisely, then I determine completely the matrix up to discrete ambiguities, okay? Because assuming that there is a mixing between cycle and third generation, okay? And this we will come back again probably in the last lecture. So in principle, 4 independent moduli, if are not chosen on the same row or the same column, are enough to determine precisely, including the phase, okay? But unfortunately, these 2 are not very precisely measured, because you should measure them from indicators that we don't control them precisely. Okay, so okay, this is just to say how we measure very precisely these entities here. And the only thing that the entities that we don't measure precisely from this type of serotonin decays are is the phase, okay? And so how we measure the phase, as you probably know, we measure the phase from loop mediated observable, in particular related to measurement response. And so to discuss that, let me now close, go a little bit further and discuss what happens beyond the phase. Sorry. There is something else I want to tell you before going to number 11. Just want to give you the basic notions of flavor physics, such that when you listen to a seminar, you are not you get everything. So I forgot to, I erased here the things. So the unitarity condition is this one. And so we have 2 types of unitarity condition. The one when I select 1, 1, okay, and that was the one I used before. For instance, 1, 1, 2, 2, or 3, which is the sum of elements on a row is 1. Or I can, if I use I different from j, I get p dagger ij equal to 0. So this is these 2 sets of unitarity conditions. This is interesting because actually these are the conditions where instead of the moduli we have the phases that enters, and in particular if we look at now, if we compute V, we dug 1 3. What we get? So we get no, sorry. Well, of course, we can also do it. This would be exactly the same, but for chronological convenience, it's better to look at this type of condition. So if I look at this one, then I can get this type of condition, which is now V dagger V 1 3, which is, so this is V dagger 1 J V J3, which is V J 1 star V J3. And so the things I'm interested here is this relation, the UD VU. So that has to be equal to 0. So you see, this is a sum of 3 complex quantities that has to be equal to 0. So historically, people think of this as a sum of 3 complex quantities that has to be equal to 0. You can always think it as a sum of 3 vectors that form a triangle. And so, if I have not erased my previous expression for the matrix expanded in power of lambda, what I would have got here was A1 minus BUD is basically 1, so this is A lambda 2 rho minus I eta plus CB squared, which is minus lambda BCB A lambda squared, and yet plus A 1 minus rho plus I eta lambda 2, and so you can check this is equal to 0. And so you see, now if I divide everything by A lambda cube, I have basically the sum of these 3 vectors in the row, in the complex rotor plane. So eta is the complex variable. So this is the vector you want, is the vector BCB squared divided by A lambda cube. This is the vector 1 minus rho plus I eta, which is this one, BTB squared, while this vector is the one related to. Okay, so this is just a pictorial view to see these elements of the Siegel matrix, and there is nothing deep beside the fact that, of course, if you measure independently these elements in certain transition, of course you want to check that they really sum to make a triangle. It is also a useful way to express the experimental constant. So when people measure, say, VUB, they say, well, we have basically measured the size of the so-called, this is called a unitary triangle, so this is the coordinate eta rho. And so, indeed, you will see, for instance, the people, experimentalists, they put a bound in this plan with eta because they measure the values of UB, or they put other bounds in this plane like this because they measure this phase here, which is the phase difference between these two elements, so it's the phase of BGPB and so on. So when you see this called secant plots of the unitary triangle, it's nothing but a way to express the experimental constraint just using this unitary relation. Okay. So here I realize that I need to make it a bit not crystal clear. So is it clear? It's a trivial thing. It's just a trigonometry. Okay. So let's now go beyond that. I want to discuss how these suppressed elements, in particular the case of these suppressed elements here, are measured. Clearly, in principle, one could measure this model from top decay. So this is a T to B, T to D decay, or T to S decay. But actually, in practice, this is impossible because the top actually strongly coupled with the couple which is 1, and these are very suppressed to bottom. And in the case of top decays, it's very difficult to identify the flavor of the final state. And also, in the case of the top, you don't have as many top as many B and T. So you cannot do precision physics with top, so we cannot measure precisely this. Yeah. It's also not the very important difference between the top and the other quarks that, in particular, the strange quark and the bottom quark are very interesting because the bottom quark can never decay into top, which would be the one where the strength is 1. Right? The bottom could decay because the bottom quark has a mass higher than charm at top, but is lighter than the top, so it cannot decay into charm and up at the 3 level, and it decays with suppressed energy. So this, remember, is roughly Cardipo square, where this is roughly Cardipo cube. Okay. So this is why we measure very precisely the suppressed elements of in the B row or B decays. And similarly also for the front stage. While in the case of the top, since it can decay to the bottom with the strength 1, this is roughly 1, clearly you will not see this subleading process. Okay. Beyond the clearly here, going back to the gauge interaction, because of this structure, clearly if I look at the neutral components of the coupled to the Z, this is remains diagonal, okay, even if I go to the mass example. So there is no 3-level flavor changing gauge interaction, contrary to the case of the data. However, there are interactions with the Z, for instance, that arise in Tafel, arise beyond the 3 level. So let me introduce the first one. This type, for instance, if we look beyond the 3 level, the process of this type, for instance, Z or the 4, okay. Let me consider the Z first. I can have a interaction of this type where here I change flavor, so I have a D, and here so I can have up, sharp, and top, so interaction W, and then I can have again flavor changing interaction, and then I can go to the D. Okay. Which is the strength? So this is an amplitude that appears at 1 level. So let me just first a very naive estimate of the size of this amplitude. So the amplitude goes like following. Clearly, let's assume, have you done a course on effective theories? Not this one. You know a little bit about effective theories? Maybe I should, okay, tomorrow I will discuss more about effective theories. Okay, in the limit where this interaction becomes point-like, okay, I basically, so in the limit where the moment of these particles are very light compared to the masses of the W here, which is very heavy, I can shrink this to a point-like interaction. And here, the interaction is an interaction of the left-handed quarks because the gauge interaction is purely left-handed. Okay? So, what I will generate is an interaction of this type. These are left. This is the only type of interaction I can generate, the structure here, and because I have a Z field, I have the 2 electron fields, they have to be left-handed, so the only type of contraction I can have is this one. Then, well, I have sum, when I have to compute this function, I will have a sum over the 3 upwards, so sum of up, sharp, and top. Then I will have a loop function, which depends on the mass of the particle that goes inside this loop, which will be the mass of let me call this I. So this is a loop function that depends only on the masses which appear here. And here, well, for a reason that I explain tomorrow, let me put a W front of this interaction. I have this type of structure which depends only on the masses, so which are the masses of the pole, which I call I, and the mass of the W, which is NW. And then I have the coupling here. So I have there is the gauge coupling, so it will be a G square. And then, well, here actually will be a G cube because there is another gauge interaction. And then there are the secant elements. So here in this case, this is V TB, sorry, V I D V this is like the ID star as I define it, and then I have the ID. Okay? Now, what is this function? Well, I don't know. I want to have I should compute it precisely, but I'm lazy, so I don't do it. Let me assume, and I will prove it now in a minute, that this function is regular when I send the masses of the port to 0. So if it is regular, it will be a constant term plus I expand it in power the port masses. Okay. Especially if the masses of the port are small, this would be a good expansion. Now, I have here the sum of these pieces here. So let me call this lambda I. Okay. I call it lambda I. So I have to sum lambda u, a term with lambda u, a term with lambda c, and a term with lambda t. But now you realize that this sum is equal to 0 because this is exactly the unitary, one of the unitary relations that I showed before. Because it's just b with dagger b t. Okay? So the sum is 0. Which means that when I now consider the three pieces, so let me do it explicitly because it's worth, okay. I just take this part here. So lambda u c plus what? Okay. It's obvious that the sum, when I take here the constant part, drops out. Okay, because of the unitary relation. So I can always rewrite it this way. So I have lambda u plus lambda c plus lambda t, the function 0 plus lambda u f of nu minus f of 0 plus lambda c f of sharp minus f0 plus lambda t f of m tau. Okay, so this is 0 immediately. Then actually, well, I did it even more complicated than it is. In first approximation, I mean the masses of the up and down port are very small compared to the mass of the top. So this is in first approximation to 0. And so I remain only with the term proportional to the top, which will give me lambda top if this expansion extends m dot squared divided by m w squared. Okay, plus something else. Okay. This is not the famous G mechanics, so you always have to look at the difference between the port masses. Actually, I could have done it even more. Sorry, I could have done it even more precise here. So even without doing any approximation, so I can always say lambda u is equal to minus lambda c minus lambda t. So I can rewrite this exactly as follows. So this is lambda sharp f of m sharp minus f of m sharp. This is the relation. And then on the top, f of m top minus f of this is basically very small, because this is basically f of 0 minus f of 0, but this is possibly large if there is a large slope to the top. Well, okay, this is more or less correct, but there are a lot of subtleties and things which are not satisfying. First of all, well, I should convince you that the function does not go to 0 when the mass of the ball goes to 0. And second thing is also, you see, it's something very strange that this diagram tends to grow with the mass of the particle running inside the loop. And this is against probably your intuition. I don't know if you heard about the decoupling theorem that tell that the effect of particle inside the loop should decouple when the mass goes to 0. This doesn't seem to decouple. And I will now try to explain why this happens and why all these things, why this strange behavior can be understood much better. But before doing that, let me look at another example where the same phenomenon occurs, which is even more interesting, which is the case of meson-anti-meson mixing. So, if you look at meson-anti-meson mixing, here, we have another type of amplitude which is peculiar and it appears only at the one-loop level. So if you get this one, so there is an amplitude where I exchange 2W, where I mix this state made of a B and anti-D quark, so this is a D bar meson, and I mix it into a so this is a B meson, and mixing with the anti-B meson. And so here I can do exactly the same thing, okay? I have the interaction here with W, and I should sum over up, sharp, and top, up, sharp, and top. Okay. So again, let's do it in first this sloping way. So the interaction which, so this will be purely left-handed coupling, double couple one of the two that works. So here, what I generate is this type of interaction twice. And now, well, for those of you who are a bit familiar with the effective theory, you understand much better why I took 1 over W squared, because here this is a dimension 6 operator, so it has to be compensated by 1 over mass squared term. I have 4 gauge coupling, so here I have G to the 4. And then I have to do twice the unitary decay, so I have to sum over I and J. I have lambda I, the lambda I is exactly this one, okay, let me write it here. Lambda I is the D I Z star D I E, okay? Lambda I, lambda J, and then I have a function which now depends on two mass ratio, because I have possible different masses here. So we can again, so just look at this part here. For the beginning, let me consider the limit where I send to 0 the mass of the upper and the chart. So I have sum over J, lambda J, and I do the first sum. So I have lambda up plus lambda chart F. So let me now call it this F I J, so I have F0 J plus lambda top F top J. Okay? And now, but this I use unitary, this is minus lambda D. So this is just sum over J, lambda top F top J minus F top 0. No, sorry, F0J. Okay. So now let's do the sum for J. So we have lambda R plus lambda char, lambda top, and so here now F top, and considering the case where J is light, so I will call top 0. Sorry. This top 0 minus F, this is 0, 0. Okay? Plus lambda top squared, now F top minus F0 top. Okay, and so now I put this here. And follow. So again, this is minus lambda t. So I have always lambda t squared terms, and I have f dt, f0t and ft0 have to be equal because this function is to be symmetric, so minus 2f t0 plus f0. Okay? Very simple. And so again, if this function do not depend on the mass, this is clearly 0, because you have a difference between heavy mass, heavy light, and light, and the dependence is 0, 0. Why? If it grows quadratically with the mass, I would expect something like that grows like a top square. Now, to compute exactly this function is very complicated. It's requires a little bit of exercise. Now, I'll show you how to do a more precise calculation in a much simpler way. And the very important thing that I also want to present, you see here, we have this dependence. So this is V, T, V star, V. So clearly, and we will see tomorrow, when we measure experimentally this amplitude, the PV bar mixing amplitude, we access directly this coupling here, VTD, which was one of the coupling of the CKMX that we don't measure precisely. Unfortunately, I've chosen a very stupid notation because I used the lambda t to define the eigenvalues previously. I hope you don't get confused. And so, how is the way to do the simple calculation? But I said at the beginning, flavor physics originate from the Yukawa interaction. So actually, if we switch off Yukawa interaction, all flavor phenomena goes to 0, disappear, all flavor mixing phenomena goes to 0. Indeed, actually, we can compute this amplitude ignoring gauge interaction. We can compute it in a limit which is called the gaugeless limit of the mode. So sending the gauge coupling to 0. Well, we have not do it to always, but we can do it for a certain class of phenomena, especially this one where we have this quark mass dependence, and this will be clear here. So let's ignore for a moment the gauge, only consider the limit where the gauge coupling is extremely weak, okay? Approximately 10 to 0. Now, in that case, still, we have an unvanishing mixing amplitude, which arises from the Yukawa interaction. Why? Because the Yukawa interaction, if you remember, has also a charged current component. But charged current, but well, the charged current is a current with a Higgs. Okay? Let me write it precisely. We get the right. So if you look at the Yukawa interaction, the charged current component of the Yukawa interaction is this one. The one that couples the left to the right. Well, okay, this P minus is the component, the charged component of the Higgs field. So the Higgs field, this one, as a bed that is. Okay, this is just the bed, okay? Now, when the bridge interaction are on, you always associate this field here, this is a massless Boston boson, to the longitudinal component of that. Okay? This is what you know that, no? Well, if you switch off gauge interaction, there is no Higgs mechanism in the sense of giving masses to the gauge field. And so the Boston boson remains massless particles. And so I'm considering that limit of the model. So here I have a massless scalar here that mediates this interaction because this is there. It's here. I don't work in that. I cannot rotate it away, this interaction, okay? Just using the longitudinal component of the data. Switch it off, gauge interaction. So this interaction remains there, it mediates this happening here. Now you see that this is much more manifest. Now I don't need to run, I don't need to work here in the cases where the up is diagonal because I'm only interested in a transition where the external forces are down. Okay. So I made here in this cases where this was here I will call it y as the eigenvalue, okay, instead of lambda. This is v diagonal I v y r v. Okay, this is what before I call it lambda. Don't call it lambda, not to get confused with this. Okay, sorry. So it's the angle, it's the one related to the mass. So here you see in much more transparent way the following thing. First of all, you see that the masses of the quarks here in this diagram appear not only because the quarks are propagating here, but also because it appears in the depth because of this curve here. And also you see that so you control the strength of the diagram, and so sending the mass of the up to 0 is just because this coupling is extremely small. So here I'm just considering the limit where I neglect the coupling of the up here because it's extremely small. And you see why the diagram is well behaved when the mass of the up goes to 0, because I have two couplings here, y up, and I have 1 over m up here in this propagator. But this is proportional to m up, so I have m up squared divided by m up, so this is regular in the limit where m up goes to 0. Okay. And this is still a naive argument. One should do it, or I can do it till the end, or just doing exactly the computation and see that the limit where the mass goes to 0 is safe. So the only coupling which is big here is the top. This is why the top right here is the relevant field. And so, when now we compute the amplitude, we compute precisely, we have this type of interaction, so we have y top to the 4 power. Okay? Then I have here my z, d, star, d, twice. Okay? I can ignore the other force. There is no cancellation between the force in this limit. There is no need of cancellation simply because each force comes with this coupling. And the coupling of the light force in the limit where the masses go to 0, they keep a vanishing contribution. So it's only the top which survives automatically simply because it's the one with the bigger coupling. Okay? So like this, and now we can do really the calculation till the end. Because this is easier. So I just put the coupling here. I have now I have a d bar left, integral d for L by d, okay? And before the propagator, so I have L is the moment I do the calculation in the limit where the external force carry 0 moment, okay? Which is, we can justify this tomorrow in terms of approximation, but I compute, if you want, it's just a limit where I compute the amplitude. So L is the loop momenta. I have the propagator on the top, and then I have the left, then I have the other spin of light, and then I have the two propagator of the ghost, which have a square. Okay? Now, we have this left-handed projection because the interaction has a well-defined character. So, let's forget now for a moment the effective coupling here. So what we have is d bar left. So clearly you see that the mass term there goes away. So I have L gamma sigma d left, d bar left, gamma rho d left. Just completing this part, okay? F sigma rho divided by okay, so these are just the propagator here. Okay, can you read it? So let's now just look at this integral. Well, before looking at this integral, this is just an integral where I have no external momenta. So this L sigma L rho can only become 1/4 G sigma rho L squared. And you see, I can even set the dimension to 4 because this integral is manifestly convertible. Because I have L squared, but here I have L squared to the 4th power, if I consider all the denominator to the denominator. So what I have is finally an answer to this y log to the 4th, d star d square, b bar left gamma mu d left square. And now times an integral. If the integral is 1/4 integral d for L of the 4th L square divided by L square minus L top square square and square square. This goes away. Go to the Euclidean. To the integral, this is really simple. You just rotate L square to the Euclidean. This is 1/4 and then 1/4. This is 1/16 pi squared. You do the calculation with just 1 over the top square. I'll show you how to do it in a few minutes. If you have difficulty, tell me tomorrow. And so this is esatto. Up to factor I. And so we got a much better result, you see. We got our amplitude is 1 square. You see, now this doesn't make much more sense because, first of all, the mass of the quarks appear in the denominator, as it should, because this is the only heavy scale in the game. And actually, the diagram decreases with the mass of the top. Of course, there is also the Yukawa coupling, and then you know the two are related, and this is the Yukawa coupling that is the one that gives the final power dependence on the mass of the quark. So now if I express the Yukawa coupling would be is the mass of the top square root divided by b, okay? So this diagram here becomes this coupling here becomes and top to the fourth, 4, 4, simplify square, so the 4 goes away, then I have b to the fourth, and top square, so the top square goes away, then I have n top square divided by b to the fourth, where b is the speed. Okay. But you see, keeping it this way, in a sense, is much more clean. You see, the diagram grows because grows linearly with decoupling, and of course there is a decoupling effect quadratic in the mass of the box. Because of the relation between the Yukawa coupling and the mass, then finally you get this growing amplitude. But you see here that cannot grow more than a top square. So previously when I did the sloping calculation, I didn't know if I had to take into account the 6 and so on. No, there is no such dependence at the one loop level if the maximum dependence is y coupling force simply because there are 4 Yukawa couplings. But if you go to higher loops, it will be higher dependence on the Yukawa, but will be suppressed because of the loop expansion. So you see, if you want, this is just an effective alpha, so it's the effective interaction, and then there is the decoupling as it should be in the mass of the top. And see that there is no W here, there is no gauge. Now, how this compare with this type of calculation? Well, here also there is no gauge, because actually these two things that once you express the W mass and the top Yukawa coupling in terms of this is not bad. Remember, this function I told you is n top square divided by n w square. So finally, I have here, I have something that goes like g to the fourth, n w to the fourth, n top square. So this is nothing but 1 over n to the fourth, which is exactly what we get here. So if you do precisely this calculation, you get exactly this result up to order G correction, so correction in the gauge cut. So this is exactly the correct result in the limit of G goes to 0. And since G, in this case, is related to the mass of the W, well, since the mass of the W is smaller than the mass of the top, if you want an expansion in small g, it's a good expansion. Small g with respect to the top in the cut. Okay? And actually, this is so I think this is a very interesting example because I told you, first of all, it illustrates that flavor fields in particular this mixing phenomena that grows with the mass of the core, they grow simply because they are related to the Yukawa coupling. The Yukawa coupling grows with the mass. Okay. And also to understand this behavior, one really has to look at to the origin of the effect which is Yukawa coupling. And when we work in this basis, where we put the Yukawa, the CK matrix in the gauge interaction, in a sense we complicate the problem because we are mixing gauge and Yukawa interaction. There are several cases where it's much easier to work keeping separately those two systems. Of course, if you want to do a very precise calculation, then you have to take into account the gauge correction. So maybe it's better to work in that case, that limit, in the full scenario. But to get the right dependence is important. And also, this is illustrative when we go beyond the standard model. Because, for instance, if beyond the standard model we break the relation between the Yukawa coupling and the mass. For instance, in the case where the supersymmetry, where particles here whose mass is not related to the Yukawa coupling, then clearly we should expect something different than what we have in the standard model. Okay, and we always should expect some behavior of this type, that the growing is related to the growing of the coupling, not to the growing of the mass. Maybe, I don't know, because probably it's good to stop here. Do you have questions?